Our second objective actually takes place later in the book. It's in chapter 6 or something. And what we're talking about here, we're defining an inverse of a function. So in this picture here, what you have is one of those, it looks like a ski lift or a mountain lift or something like that. And one side's going down, and you see this chick with her fabulous shoes and maybe a small little foot tattoo. She's going down one way, and if she ever wanted to come back, she would go on the other side. One goes down the mountain, the other one would come up the mountain. One does something, the other one undoes something. And that's exactly what inverses do, is they undo what you just did. So let's look at something from geometry here. So let's suppose we drew ourselves a triangle in the coordinate plane. You can see it right there, it's graphed. What would happen if we were to take the x and the y coordinate and we would switch places with them? So down at the bottom you see that little mapping there. xy gets mapped to yx. If you switch those coordinates, what happens? Think about it for a second. See if you remember from geometry what happens. Well, this is what happens. If you switch, for example, the point 1, 4, it becomes 4, 1. And so on. What you've just done is you've reflected that graph across the line y equals x. Now I start off with this because that's exactly what inverses do. They switch the x and the y coordinate. And if you switch the x and the y coordinate on a graph, it reflects your graph across the line y equals x. So here's an example of an actual function. So the function is the kind of grayed out looking one, and you have the point AB on it. If I were to switch the x and the y coordinates, that reflects it across the line y equals x, the red line, and the point now becomes BA. And here's the little notation for the inverse of that function f of x. It says f negative 1 of x. That negative 1 is the symbol for inverse. Okay? So, in this exercise, we're going to let f of x equal 2x minus 4, g of x equal a half x plus 2, and let's just find these two function values, and then it says, explain the significance of your answer. Well, we'll just have to see what happens. Okay, so f of x is equal to, whoops, not of x, how about a 5? Email. 2 times 5 minus 4, that's what I want to calculate. I get 10 minus 4 is equal to 6, so this corresponds to the ordered pair 5, 6, right? Alright, let's switch colors. Red, make this nice and Christmassy. G of 6 this time, let's take a half of 6, add 2 to that thing. We have 3 plus 2, which is 5, and that corresponds to the point 6, 5. Curious. What happened is that the x and the y coordinates switched. X and y switched. Well, what does that mean? What I was just explaining to you before, that must mean that these things are inverses of each other. On the first function, if you input the number 5, you get 6 out. If you take the inverse and you plug in the number 6, you get 5 back. Okay, a follow-up question. It's still the same two functions. I want you to graph them on a coordinate plane. So graph them on a piece of graph paper and try to see what you notice about the two graphs. Okay, so you go ahead and pause it and you graph those on your own. Alright, so graphing these two equations, this is what you should come up with. And then if you were to notice, the red one is a reflection of the green one across the line y equals x. Just take a look. If you were to graph y equals x in there, you could see they're the exact same distance apart on either side. Also, this illustrates what happens when you have two inverses and you graph them both together. Okay, so before we give the actual definition of inverse functions, let's first talk about this thing called function composition. So function composition happens when you take a function and you substitute that whole entire function in the place of x in another function. Like this. This h of x is made from, or It's made from the composition of g and f of x. You take all of f of x and you plug it in for x into the exterior function g of x. F of x, it's on the inside, it's called the interior function. It gets plugged in for x in the exterior function, which is on the outside, g of x. Okay? I know this seems like a weird thing, but we've already done, we've plugged things in for x and we've simplified before, so this is just another one of those things. Okay, so let's try it with the two functions that we've been working with so far. We're going to do these compositions. So the first thing that we're going to do is we're going to take all of g of x and we're going to substitute it in for x in f of x. We're doing it in that order because g of x is on the inside, so it goes in for x. So this will be equal to 2 parentheses. Now I'm going to take this whole function and stick it in for x. 1/2 x plus 2, close the parentheses, and then minus 4. Now watch some magic happen. So distribute your 2 through here. We have x plus 4 minus 4, and all of this simplifies down to just x. Okay, now let's go in the opposite direction here, like so. With let's go with red here. This time I'm going to take all of f of x, it's on the interior, and we're going to plug that in for x in the g of x function. So this will be equal to, this time a half goes on the outside of the parentheses, 2x minus 4, all of this plus 2. Distribute the half through here, and we have x minus 2 plus 2, which is equal to x again. Okay, so this is something else that will always happen if two functions are inverses of each other. And as a matter of fact, this is how we define inverse functions. Okay, so before we talk about inverse functions, let's just talk about them as relations first, because every function does not necessarily have an inverse who is a function. It might be only an inverse, a relation. Okay, so an inverse relation and its relation just switch the x and the y coordinates. One of them undoes the other one. So inverse relations undo each other. Just for example, let's take a look at this ordered pair 1, 4. In the original relation, you input the number 1 and 4 comes out. If I have its inverse, I would put in the number 4 and 1 would come back out. I would get the original input. Okay, so think about this thing called cryptography. In cryptography, you have a secret message. So you take a message and you put it in code. And then you send that code someplace to somebody. Maybe it has your credit card information or whatever. Maybe it's over the internet. So whoever receives it, if you want them to be able to decipher it, they have to be able to undo it to get the original credit card information out of it. And that's what happens with inverses. Okay, so here is the actual definition then of inverse functions. If a relation and its inverse are both inverses, or they're both functions, then they are called inverse functions. And this is what has to happen. If you do this thing, you put f inverse, that's the inverse, into the original function, that's function composition, you get x back. And you do it in either direction, it doesn't matter. They will undo each other. And then again, there's that notation, f with a little -1 is read f inverse, or the inverse of f. Okay? All right then. So, just keep this in mind, that the inverse of a function is not necessarily a function. So what we have here, instead of having cable cars that are going up and down a mountain, you have a zip line. And on a zip line, you could go down the zip line, but you don't have the same exact or a similar way to go back up by that zip line. You're not going to get back up that way, right? So there isn't an inverse in that case. You actually have to climb the mountain again. Okay,